All right, everybody, we're going to move on a little bit, okay? And just to tag on to the last lesson, we talked about the factors that affect whether something's going to dissolve in a solvent or not. Is we want to look at also how fast something dissolves. I know sometimes we sometimes are concerned with the speed of something dissolving. This could be taking a vitamin or some medication, and the time it takes for that to get into your system to hit that part of the body it's affecting sometimes can be a concern. I mean, again, sometimes we want to speed up or slow down something that's dissolving. So what would affect this in a way? Okay, so we look at the rate of solubility or the rate of dissolving. And a lot of this is kind of common sense. So if you think about it, there's a few things that we can do to increase or decrease. So we're going to look at the increasing the rate of solubility. Of course, if it went backwards, you could decrease it. But so sometimes we like to dissolve into something solution faster, okay, or slower, depending what it is. Okay, the rate of dissolving, okay, is going to increase, okay, for anything that maximizes the contact of the solute and the solvent. So that's going to be really, really important. All right, so if you can maximize that contact and maximize that energy, you can dissolve things faster. So that becomes the big thing. So one of the things we can do is crush the solid solute. So if you have a solute that is in large chunks or large lumps, if we crush that up a little bit, you can increase that surface area a little bit, okay, and allow that to dissolve faster. When we talk about powdered sugar versus sugar cubes, you could probably realize that a sugar cube versus powdered sugar in small little particles, the sugar that's chopped up here would probably dissolve a lot faster. Okay, we could talk about agitation or stirring the solvent mixture. Okay, if you mix that around really well with a stirring rod or your spoon, or you can mix it as long as you mechanically move it, you're allowing the contact between the solvent and the solvent. So as long as you have more contact between that solute and solvent, you can effectively make it dissolve faster. You can also increase the temperature. So increase the temperature, again, you're adding that higher kinetic energy. The particles are going to move faster. When they move faster, they have more collisions. When they have more collisions, they're more likely to dissolve and form those new attractions. So important to know about this. Okay, and don't forget those gases, right? Gases, you increase that pressure, you limit the space between them, right? You can limit the space. Okay, there's more contact. All right, you can have more contact between those particles. So again, very common sense here. Think about what the particles are doing in their contact, and you can realize this. And again, if you wanted to go backwards, that would work as well. Okay, again, surface area. Something in this picture you use is low surface area. Your solute molecules are your blue ones. Your red ones are your solvent. And notice with a large surface area, those particular solvent molecules cannot contact the solute very easily. They can only contact from the outside. They can't penetrate inside. However, if you break this up a little bit, you'll see that the solvent molecules can really get around and contact all of the solute molecules quicker, okay, or more effectively, and then you can have more of a higher surface area. Okay, so that's important to know about this. So just really a tag along from the previous lesson. Okay, next we want to switch gears a little bit and talk about something called a solubility curve. All right, and this is going to be really important to know, so you definitely want to buckle in on this. Make sure you're taking good notes. Make sure you're listening, and if you have to go back, check on it. So what we can do is we can look at the quantitative measurements, okay, of putting a solute in a solvent. And what we do is as we add more solute to the solvent, to the same amount of solvent, and that's the key here, as we add solute to solvent, okay, we increase the concentration of the solute. All right. We eventually do reach a point where you cannot dissolve any more solute. You reach a maximum point. All right, and that becomes a very tricky part to adding solute, because you reach this point where you can't dissolve anymore, and this can be effective for certain situations. So we'll have to take a look at this phenomenon. All right, so we look at something called a solubility curve, and a solubility curve is simply a graph which looks at the temperature on the x-axis, okay? On the x-axis here, temperature going to the right here, and on the y, we're going to have the grams of solute, so the amount of solute that you're dissolving, okay, in a specific amount of solvent, okay? So that's important to know here. So there's really three things going on here, and you really have to be careful about this, because these three situations, these three ideas can change, and when they change the solution. All right, so again, temperature is one variable. The amount of solute that you're adding is another variable, okay? And the amount of solvent is also the third variable. Now, what we're going to do for the sake of this graph is we're going to leave the amount of solvent the same. So we're going to assume that the solvent is staying at 100 milliliters of water or 100 grams, which is the same thing. So we're not changing the solvent. That's staying constant. And simply what we're going to do is we're going to dissolve solute in it, okay, at these various temperatures. And what we're going to do is we're going to graph where we hit that maximum amount, okay, where that maximum is. Okay, so let's describe what we're going to do here. Well, let's just start from the beginning. Now, if you look at the graph, there's three places you can be, right? You can be on this line, okay, and we'll talk about that line in a minute. We can be in a position where below that line, we can be the amount of solute below that line, or we can have a certain amount of solute that's above that line, or we can also be on it. So we're going to describe the three different types of solutions you can possibly have when it pertains to a solute dissolving in a solvent, okay? All right, so at point A, where are we? Well, basically, we have 100 milliliters of water, okay? And we're going to put 150 grams of this solute in it, okay? And let's just say we're going to be using sugar at this point. So if we put 150 grams of sugar, so I'm not going to use the salt line, I'm going to use the sugar line. So if I put 150 grams of sugar in here, I would be at point A, and I would be below this line. And what that would be telling me is I actually has less than the maximum that I could fit in the solution. Okay, that would dissolve. So that means I can continually dissolve solution, okay, or I'm sorry, solute in that. So I basically have room, right? I have room to dissolve more, okay? More solute could be added, okay? How much more would be the difference in those 2 points, okay? And we have a special name for the solution in this position, okay? And this is called an unsaturated solution. An unsaturated solution is a solution when you can add solute to a solvent, but you still have room to add more. And there are many positions to be unsaturated, right? We can be anywhere from, a very small amount of grams of sugar to very close to 200 grams of sugar, 199. Okay, in that case, you can still add more. And what would happen is more would dissolve. Now, as we get closer and closer and closer, and we go in this direction, closer to this line, eventually it's going to be harder to dissolve that solute until we reach the maximum amount that we can dissolve, okay? So when we hit the 200 gram mark, that becomes the maximum amount of solute that you can dissolve at a given temperature, okay? Again, we're staying at 20 now, okay? And at this point, no more solute can dissolve. Now, if you do add more, that solute is simply going to go to the bottom and collect at the bottom as a precipitate. All right, you can call it that, or you can just say it's called undissolved solute. All right, and that's called a saturated solution. Now, a saturated solution is very special because it's a certain special kind of thing happens at saturation. You reach a point at which you reach an equilibrium position where you have equal rates of change. Now, what do you mean by rates of change? What changes are we talking about? Well, what happens is, in this case, if you add more solute, it actually goes and sits at the bottom, but it really does dissolve and recrystallize at the same time. So basically what you have is a strange situation here. You have the solid that's sitting at the bottom is going to dissolve at the same time that dissolved solute is going to then go and recrystallize, okay? And that only happens at the saturation point, okay? So inside the solution remains constant. The concentration of the solution remains constant, which means the amount of dissolved solute stays at 200 grams, because if you add any more, it'll fall to the bottom and you will form more crystals at the same time that you dissolve. So if you do that at the same time, this 200 grams remains constant. Okay, so I'm going to show you a little clip on this, a little video on the clip, so you can see this actually in action. But that means you're on the line. So what's so significant about this line is that this ends up being something called a maximum. So this becomes a line of saturation. Okay. Now, if you change the temperature, you can see this saturation line actually rises, which is telling us something from the previous discussions. We said that, as you raise the temperature, you can dissolve more and more solute. And that's going to be true from the discussion here, because if you start at 20 and you moved on to 40, you'll see that the sugar solution can actually hold more now at a higher temperature. Your saturation point increases. Now, different substances will have different saturation lines. Okay, notice that salt is relatively flat, while sugar, rises increases pretty greatly as you go to higher temperatures. That means a sugar solution can hold more solute than a salt solution at the same temperature. All right. So to repeat, an unsaturated solution can still add more, and then you reach this point where you're on the line, okay, which would be your saturated solution, okay, and at that point you can dissolve no more when you're locked in at 20. Okay, really important. Okay, so how do you actually get more? I mean, if I'm sitting here telling you that I can't, if I add more, and 200 is dissolved, and I'm kind of at that limit. Well, how can I actually ever get to C? Well, if you stay at 20, you won't be able to get to C. But there's a little trick that we can do. All right, so I want you to really pay attention to the next one. If you take a look at this, let's just say we start at point B. Okay, so I'm just going to repeat what we're doing here. All right, and what we have is 200 grams. Here we are, 200 grams on the graph. We're on the line at 20, so we're saturated, right? Okay, and let's just say I add 100 grams more solute. All right, now think about what that would do. If I stay at 20 and I add 100 more grams of solute, if you guessed that that would fall at the bottom of the flask, you'd be right. So if I add 100 more grams of solute, it's going to go to the bottom. So my 100 grams is actually going to sit right there at the bottom of the flask. Because again, 100 plus the 200 would be 300 total here, with 200 dissolved as AQ, but 100 sitting at the bottom. Okay, and again, that shouldn't be a shock because at 200 you've reached the max. So anything extra would be at the bottom. However, here's something interesting that we can do. If I wanted to dissolve this, I would have to heat it. And if I heat this and I move it over to 60 Celsius, okay, sorry, at 65, so if I go here to 65 and I raise the temperature here to 65, which is right about, this would be 70, this would be 65. If I check this, I will find out that I am saturated again at 65. All right? So at 65 Celsius, this container now contains 300 grams of dissolved solute, and effectively I've dissolved those crystals, okay, by heating it, which you'd expect. All right? So that's going to become a real important part. Now, it's all going to dissolve now at 65. Now, there's two things I can do. All right? We know that if I was to cool this back, all right, if I take this guy and I cool him back to here, that would be scenario number one, right? So I could do that. If I cool it back, what would you expect? Well, you would expect that the crystals would be reversed, right? If I went back the other way, the 100 grams of crystals would fall out, okay, and become solid again, because at 20, I can only fit the 200. Okay, so think about that again. If I had 300 grams dissolved at 65, and I go back to 20, since I'm only can dissolve 200, then 100 grams must come out as crystals. Okay, they're still in the beaker, but they're in these crystals. However, sometimes, and that would be the first what you'd expect. However, sometimes something interesting happens, and what happens is we go backwards and we cool, but the solute does not come out. It actually remains in the beaker dissolved. Okay, if I slowly cool this back. If I cool back to 20 very, very slowly, if I cool back 20, okay, sometimes more than the maximum stays dissolved. Okay, and this is going to be an interesting point when if more stays dissolved, okay, then the 300 stays in there. Okay, and it kind of gets stuck. Okay, and this is a very unstable solution because the 100 grams of crystals would normally come out, but if I cool back very slowly, okay, and I don't disturb the solution, I keep this very, very, very clean. I keep the glassware clean. I keep the solute and the solvent are very pure and clean. Sometimes those crystals don't have a chance to precipitate. They don't have a place to gather around. They don't have a way to, interact. And form crystals. Okay, so this becomes a very unstable solution. Now, crystals will reappear if the solution is disturbed. Okay, and the name of this solution, in this particular way, is called a supersaturated solution. So a supersaturated solution, of course, the prefix super means above. Okay, and now how we reflect that in the graph is we see a position above the line. So up here would be a super saturated solution. Okay? This would be unsaturated solution. Okay, so a quick review on this. Okay, an unsaturated solution is one that has not enough solute in it. You can still dissolve more, so there are many unsaturated positions. Okay, at that temperature, at the saturation point, there is a maximum. There's only one saturation point at a particular temperature, and that is done by experiment. Again, this is all done by experiment. Okay, don't forget there is dissolving and crystallizing taking place at the same time at a saturated solution at equilibrium. Okay, so that would be on the line would be saturation. Okay, now if you take a saturated solution and you add some more solute, you'd expect it to go to the bottom. We would. Okay, and if you heat that solution to a higher temperature, you will dissolve that solute. However, if you cool it back slowly and carefully, you can cause that extra solute to stay super saturated in the solution. Now, if it stays in there, what you can do is if you do this, if you take this unstable solution and you add solute to it, okay, you can get the crystals to come out and reform again, okay, if the solution is disturbed. Okay, and you can disturb it by adding something called seed crystals. Now, if you add seed crystals to them, I think I spelled that wrong, crystals to this, you can get this solute to dissolve. Okay, so that's, I'm sorry, you can get it to form crystals and come out of solutions. That's a really interesting way to see it. And what I might do is I might post a video up on modules so you guys take a look at something that would be something that would be a super saturated solution. All right, so that'll be it for today. And what I want to do is just really quickly is I want to show you a particle model of this so you can see this in real time. So if we take a look at over here and we bring up this little video, I want you to take a look at this. And this is a little beaker of a little tank of water here. And of course, the blue section corresponds to water. And I just want to take a really quick look at this and notice a few things. If I take the salt shaker and I give you a little shake on this, okay, and I shake this salt shaker, okay, I can get this NaCl. If you're counting the dissolved ions here, we'll see that when those ions hit the water, you create this unsaturated solution. Okay, and how I know that is that if you can figure that out, that as you add salt, as long as that salt continues to dissolve, okay, that means I can keep fitting more. All right, so you can see as these crystals hit the water, they separate, they become homogeneous mixture, they begin floating around here. Water molecules will separate them and attract to them and keep them separate. And you can see they keep moving. There's always moving ions here in solution. Okay, and I can just keep adding this, and I would keep adding these crystals and keep adding these crystals over time. Okay, and it gets kind of crazy. And if you notice also, if you take a look at the count here, you'll see the bound ions in the solid state now become 0, right? And you could see the dissolved ions. It's actually putting a count on this. So I'm going to keep adding. And we'll see that I keep adding more. You can see the bound means the solid state. And I can keep adding more. And you can see as it hits the water, the bound ones are dissolving. And they're going down as you get more and more dissolved ones. And you're getting kind of concentrated. So this is how you concentrate a solution. You keep adding solute to the same amount of solvent. Now, the little bit of error here is the fact that this is probably should start rising. The volume should go up here, but in this video, they're just showing you the particles. So again, I'm going to start adding. You can see it's getting kind of crowded in there. You're getting to a point where it's going to be a little bit more difficult to add this. And again, because I'm posting this and recording it is the reason why it's lagging a little bit, but you're still getting the same effect as we do. So I'm going to keep adding this extra solute, and I think we might get into the point where this is getting to the bottom, and you can see that we've kind of hit the point where we still have now solid collecting at the bottom of this container, all right? And important thing now is that if you look at it, the bound solid has some solid to it. So now, no matter what I do, this is now hit the saturation point. All right, so this is the saturation point when you add solid to a solution that no longer will dissolve. All right. And again, this is an experimental thing. You wouldn't be able to calculate this. You would have to do this by experiment. Now, one last thing I want to note on this before we end is take a look at the surface of this solid. And what you're going to notice is that you may notice a little bit of particles leaving the solid as particles from the solution are jumping back on. So we just lost a particle there, and now we gained a particle there. We lost a particle, we gained a particle, we lost a particle. And this idea continues forever. So if you look up here, you'll see that the amount of total solute that's dissolved is balanced by the one that's bound. All right. So, but you're still getting dissolving and crystallizing. So as ones jump off and dissolve into the solution, you'll have ions that jump onto the crystal and crystallize. And that's what I meant by the equilibrium. You get this changing of the solid and the solute. Okay, it dissolves solute in the solution, and this is the saturation point. So really, really important that you understand that that's what the saturation point is. So I wanted to share that with you so you can see it visually. All right, and again, this goes on forever. Okay, one thing I also want to note while this is here, if I do add more solvent, and I do add more solvent to here, and I add more water, okay, I then can change the saturation point again. So again, now that crystal will now dissolve. Okay, if we add enough water to this, okay, and you can see the crystal starts to dissolve. So again, when we define a saturation point, we want to define the amount of solvent and the temperature so that we make sure we find the accurate saturation point. All right, I hope this helps. If you have to go back over and take a look at it, have a great day, everybody.